Okay, for example 3, here we're going to sketch this product function with, it's got a root of something, so it's going to be a little strange for us. Okay, following the curve sketching algorithm to an extent, I am going to first look at the domain. So here, because I've got a root sign, I have to make sure that everything inside here is either going to be 0 or positive. So I can't have any negatives, which means that my domain then has to be everything that is less than or equal to a 2. Okay, so we have to really keep in mind that we're restricting lots and lots of values then. In terms of x-intercepts, well, this could be a 0 if x was a 2, and this could be a 0 if x was a 0, so I've got those two as x-intercepts. In terms of y-intercepts, whenever x is a 0, so my y-intercept is also going to be at the origin. In terms of asymptotes, well, this thing can't really have any asymptotes. There's a bunch of different ways you can figure this out, but kind of the main reason is with the product that's here, this function doesn't have an asymptote, this one doesn't have an asymptote. In terms of the restricted values, the only potential for anything would be at 2, which we just said was an x-intercept, so it doesn't really have anything there. Okay, so let's get into the derivative portion here, because this is going to get messy. Because this is a product, we're going to use product rule. So I'm going to take the derivative here of x, and then times this, and then I'm going to add that to the same thing with the roles reverse, x times the derivative of this, which is going to need a chain rule. So the half coming down, and then we're subtracting the exponent by 1, and then the derivative inside is a negative 1. Okay. And now this is going to need to be simplified. So how I've done this is I just rewrote this a little bit, and I'm going to combine these, but there's other ways you can do this as well. So I just rewrote the negative exponent so it looks like it's rational, and then I combine them with a common denominator, and then I can simplify it. Okay. Then from here, when it's simplified, I'm going to be looking for critical numbers. So I'm going to look for where the numerator could be 0, which there's potential there, or where the denominator could be a 0, and here we have to pay attention to something. So I've got my critical number where the numerator is 0, but where the denominator is 0, that's x being 2. Typically this would be a critical number to consider, but in this function 2 was something very important for us to be aware of, because based on where the domain is, this is an endpoint, which means that our function can't really be differentiated there. And the reason why it can't be differentiated there is if you go all the way back to what we talked about in kind of the first unit, that derivatives are in essence just a specific type of limit, and for limits to exist, we need the limits to exist on both sides of whatever we're approaching. So here this is only kind of defined on one side, so if we're looking at the slope of the tangent, then we can't have slopes of tangents from kind of both sides of 2 corresponding to the same value or converging on that same value. So endpoints, they get rejected. And I kind of made a note here for that, so it can't be a critical number. In terms of possible points of inflection, then I'm going to take my first derivative, I'm going to have to take the derivative of this thing, which will be a fairly complicated process now, because that thing's going to use a quotient rule, and I'm going to have some roots and some negative exponents go in, so be really, really careful along the way. So if I take the derivative of the numerator times denominator, subtract, then numerator times derivative of the denominator, so that 2 is just going to kind of be in there hanging out, and then take the chain rule of the root of 2 minus x, okay, over the denominator squared, and don't forget that 2 is also going to get squared in the process. Okay. So in my next step, what I've done is I've just simplified this a little tiny bit. I expanded that. I collected a bunch of factors just to make it a little bit easier, and I changed that sign because of the negative, and then I squared everything inside here. Okay. Now what I'm going to do is I'm going to common factor, so I'm going to take out, in this case, the smallest exponent as my common factor, the 2 minus x as to the negative 1 over 2, that's the smallest one, or the most negative one. And then everything that's left, after that, I'm going to collect, and that because it has a negative exponent, I can move down and it'll collect with the 2 minus x. Okay, and then that will simplify my second derivative, which means now if I want to find possible points of inflection, I will look at the numerator and see where it's 0. I will look at the denominator and see where it is going to be giving me some restricted values. So here is another thing that we have to be concerned about for this example is, yeah, I can get a 0 from my numerator, but actually that number is outside of our domain, because our domain was everything that was less than or equal to 2. This is greater than 2, which means even though it is a 0 for my second derivative, I don't have to consider it because it's not part of my graph. My graph's only going to be going up to and including 2. And then 2 again is an endpoint, it can't be a point of inflection. So then what that means then is that we're going to have to chart out the information from our critical numbers and from our point of inflection with our first and second derivative. So let's look here. I'll put this right alongside it. So here's my first derivative. I've got its factors going in. I've got my domain, which goes up until 2. I'm just going to keep that as a soft bracket, so you can imagine kind of just an x being 2 over here, but nothing's really there other than the point. But I will fill this in, and I will populate it here with my summary. So my first derivative is telling me that my function is going to be increasing and then decreasing. So here I should have a local max. And in terms of the second derivative, let's move that here. Here's my second derivative. I'm going to put in its factors and then get the summary once it's populated, which then here, if I look at the summary, this is saying this is always concave down wherever it is defined. And if we join these bits of information up, I put my little summary that I usually do, then we can sketch out what this function is going to look like. And when I sketch out what it's going to look like, what I'm going to do first, I'm going to put in my x-intercepts. I'll put in my y-intercept if it's any different. I don't have any asymptotes to put in. I already analyzed my critical numbers and my possible points of inflection. I have one key point to put in besides those x-intercepts, and then I'll put in the shape of the graph, which should look something like that. It's kind of anticlimactic, but that's what we analyzed and what we were able to decipher. So I've got my x-intercepts, I've got my one other key point. This thing is increasing and then decreasing, but always concave down. And then it stopped at 2.